Okay guys, so as you can see, our today's topic is thermodynamics. Before we proceed for the video, I would suggest everyone to go through the basic terms that are used in thermodynamics, like what is system, what are surroundings, what do you mean by intensive and extensive properties, what are reversible and irreversible processes, because in this video we have discussed only the conceptual parts. So once you go through the basic terms, the video will be much more clear and much more easier for you to understand. So let's start. First we have modes of exchange of energy. So there are two modes of exchange of energy. One is heat and the other is work. So heat is the energy transfer between system and surroundings present at two different temperatures. Okay. So suppose the system is at temperature T1 and surrounding is at temperature T2. So heat flow will occur from system to surrounding or vice versa until the temperature of both system and surrounding gets equal. That is, equilibrium is being attained. Suppose system is at a higher temperature, system will eventually lose heat, come down to a lower temperature, and this process shall continue until the temperature of both system and surrounding gets equal. Coming to sign conventions, we have heat absorbed by the system as positive and heat released by system as negative. So you can memorize in this manner. System absorbing heat can be compared to system gaining something. So gaining something can be treated as positive. So in that way, heat absorbed by system is positive, and similarly system releasing heat can be compared to system losing something. So losing something can be treated as negative. So heat released by system is negative. Okay. Next mode of exchange of energy is work. So work are of different forms such as electrical work, mechanical work, or PV work, that is the pressure volume work. Now, pressure volume work can occur only in gaseous systems, okay? And the condition is that there must be a pressure difference between system and surroundings. Just as in case of heat, there should be a temperature difference between system and surroundings. So for PV work to occur, there must be a pressure difference between system and surroundings, and it will involve change in volume against the external pressure. Coming to sign conventions, you can see work done on the system is positive and work done by the system is negative. So also you can see I have mentioned the frame of reference that is used in chemistry. So the frame of reference used in chemistry is system. Now if you have already studied thermodynamics in physics, or eventually while you will be studying thermodynamics in physics, you will find that the sign conventions are exactly opposite than that used in chemistry. So to note, we have work done on the system is negative in physics, whereas work done by the system is positive in physics. Also, the frame of reference is different, right? The frame of reference that is used in physics is surroundings. So, frame of reference is actually the viewpoint, that is from where you are viewing the system. So, in chemistry, you are viewing the system from being within the system itself, whereas in physics, you are viewing the system from the surroundings. Since the viewpoints are different, that is the frame of reference are different, the sign conventions are opposite in chemistry and physics. Okay, so if you have any doubt regarding understanding the sign conventions and what is frame of reference and why the sign conventions are opposite in chemistry and physics, you can comment down below, and then I can make a separate video regarding the sign conventions that are used in chemistry and physics. Okay, for now, let's proceed. Coming to the expression of PV work, let us consider an ideal gas enclosed in a cylinder fitted with a movable piston. The cross-section area of the piston is A. the internal pressure or pressure of the gas is mentioned as P internal. The external pressure on the piston is Px. The initial volume of the gas is V1. As per the condition, external pressure is less than the internal pressure. So this will force the piston to move upwards through a distance d until the pressure inside and outside the container gets equal. Now volume has increased, expansion has occurred, and this is work done by the system. Or as per the sign convention, work done by the system is negative, so this is a negative work. Coming to the equation, work equals to force into displacement, that is F into D. Now force is equal to pressure into area. So in place of area, we have mentioned A, that is the cross section area of the piston, and in place of pressure we have mentioned the external pressure because volume change has occurred against the external pressure, right? Putting this equation in place of F, we have got this equation. Now see, AD I have mentioned is the change in volume, that is delta V. So this is the A, cross section area of the piston, and this is the distance moved by the piston, that is D. So AD is actually the change in volume from V1 to V2, that is delta V, right? So we can write delta V in place of AD. So what we have got, what is equal to external pressure into delta V. So I have mentioned the expression from the previous slide. Okay, now I will check if this expression satisfies the sign convention for expansion or not. Now from the previous slide we have seen that there has been increase in volume in expansion, that is the final volume is greater than the initial volume. So change in volume or delta V is positive. Pressure value is definitely positive. So in total we are getting a positive sign for work done. But we know expansion work done is actually negative work. So this expression is not satisfying the sign convention, right? So to satisfy the sign convention, we must introduce a negative sign in the expression. So now we have introduced a negative sign in the expression. Now let us check whether the sign conventions are getting satisfied for expansion work or not. So as we know, delta V is positive for expansion. Pressure value is definitely positive. And we have a negative sign in the expression. So in total, we are getting a negative sign for work done. So yes, the sign convention for expansion work is coming out to be negative, and this equation is thus satisfying the sign convention. Now let us find out whether this expression will satisfy the sign convention for compression or not. Okay. So compression is actually decrease in volume, right? That is the final volume is less than that of the initial volume. So your change in volume or delta V is negative. Okay, so this is negative. Pressure value is definitely positive. We have a negative sign in the expression. So in total we are getting work done value as positive. And as we know, compression work is actually work done on the system. And the sign convention is positive. So yes, the sign convention is getting satisfied for compression work also. So we can say that this expression is satisfying the sign convention for both expansion work and compression work. So the generalized equation will be W is equal to minus external pressure into the change in volume, right? Okay. Now this expression holds true for irreversible expansion also. So what do you mean by irreversible process? Irreversible processes are unidirectional single step process. So unidirectional means that path of the process will not be reversed, right? So in irreversible processes, the change in volume will occur against the external pressure in single step only. So this expression will also be true for irreversible expansion. Okay. Now coming to free expansion of ideal gas. Okay. So free expansion of ideal gas means expansion in vacuum. Okay. That is, there is no external pressure. P external is 0. Now if you see this expression, if P external gets 0, work done will automatically be 0. So you must remember that for free expansion of ideal gas, work done is 0. Now coming to work done in isothermal reversible expansion of ideal gas. Now for reversible processes, we know the change is carried out in several small steps and in such a manner that the initial conditions can always be restored by an infinitesimal change, and that the path could always be reversed. Okay, so now if we plot the PV curve for reversible expansion, pressure will be on the y-axis and volume will be on the x-axis. Now we know for expansion, the final pressure must be less than that of the initial pressure. So yes, here we can see that the initial pressure has a higher value and volume increases in expansion. So V2 is greater than V1. So from initial point A to final point B, we can see that the pressure has decreased from Pi to Pa and volume has increased from V1 to V2. But the entire process is carried out in several small steps, right? So here the entire process has been carried out in 7 small steps. Okay, now to find out the net work done, we need to find out the work done for each of the small steps, right? So if we need to find out the work done for first step, let's see how we can find out the work done. So for the first step, you can see the pressure has decreased from Pi to P1. This is P1. And volume has increased from V1 to say VA. So change in volume is delta V1, right? Now we know the expression for work done is minus P external into delta V. So the volume change against the final pressure, right? So for the first step, work done will be W1 is equal to minus P1 into delta V1, where P1 is the final pressure against which the volume change has occurred and delta V1 is the change in volume for the first step, right? Now similarly, if we need to find out the work done for second step, so we can see pressure has decreased from P1 to say P2 and let volume has increased from VA to say VB, and the change in volume is delta V2, right? So work done for second step is equal to minus P2, where P2 is the pressure against which the volume change has occurred, into delta V2, where V2 is the change in volume for the second step. Correct? Now similarly, we can find out the work done for each of these small steps, right? For all the 7 steps, we can find out the work done in the similar manner. Okay. So what can we understand from this? That the net work done will be the summation of all the minus P delta V values for all the small steps, right? So net work done is summation of minus P delta V for each small step. That is, this is the expression. W equals to minus summation external pressure, that is the pressure against which the change in volume has been achieved, into delta V. Now we know for reversible process the change is actually carried out in infinite number of steps. So to find out the net work done for infinite number of steps, we cannot use summation of all the steps, because summation can be used only when the steps are finite. If the steps are infinite, we need to integrate all the steps to find out the net work done. So for reversible process, we need to actually integrate all the steps because they are carried out in infinite number of steps, right? So mathematically, we can write the reversible work in this manner, where summation is replaced with integration from V1 to V2 and dV is the small change in volume, right? Now we know for expansion, external pressure is less than internal pressure, or P external is equals to P internal minus dP. For compression, external pressure is greater than internal pressure. So P external is equals to P internal plus dP. Now if we combine these two equations, we will get P external is equals to P internal plus minus dP. Now if we put this equation in this expression, what we will get? We will get this equation, right? Now if we multiply dV with each of these terms, we will get this expression. Now we know dP dV is very small. So this part can actually be neglected, right? So finally we'll get this expression. Okay. Now this is the expression which we have obtained in our previous slide. We know for 1 mole of ideal gas, P internal is equals to RT by V. So if we put this expression in the previous equation, we will obtain this. Now we know R is a constant, so it can come out, right? T is also a constant because it is an isothermal process, right? So T can also come out. Now if we integrate from V1 to V2 for dV by V, we can write it as ln V2 by V1, because integration from V1 by V2 for dV by V term is actually equal to ln V2 by V1. And if we convert it in terms of log, we will get minus 2.303 RT log V2 by V1. Now for n moles of gas, W reversible is actually equal to minus 2.303 nRT log V2 by V1, or in terms of pressure, if we write, it will be equal to minus 2.303 nRT log P1 by P2, right? So as we can see the statement that for expansion, reversible work done is maximum work done. So we will prove this statement first mathematically and then through graphical representation. So first, from mathematics point of view, see, we have obtained this equation from previous slides, right? Now we know that for a given change of volume, work will be maximum only when the pressure value is maximum, right? That means work will be maximum only when P external is maximum. For reversible expansion, we know that the condition is that the external pressure is less than that of the internal pressure by a very small amount, delta right? So Px is equal to Pn minus delta P, and we have got this equation in previous slides also. Now if we put A in equation 1, right, we will get this equation, right? Now we know delta P is infinitesimally small because in reversible processes the conditions are such that the initial condition can always be restored by an infinitesimal change, right? So we know that the pressure difference is infinitesimally small. So this delta P value can be neglected and P internal minus delta P is almost equal to P internal, right? So what will happen to equation A? Since delta P can be neglected, Px will become almost equal to P internal, right? And what will happen to W reversible? Since delta P can be neglected, W reversible will become equal to minus P internal delta V, and also since P external has become almost equal to P internal, so in place of P internal we can write P external, or W reversible will be almost equal to minus P external delta V, correct? Now we know for a given volume change delta V, let us say Px is maximum. Now if Px is maximum, we know work will be maximum. That is W reversible will be maximum, denoted as W max. So W max will become equal to W reversible, which is equal to minus 2.303 nRT log V2 by V1 obtained in our previous slide, right? Now coming to the graphical representation. So first we will discuss the graphical representation for reversible and irreversible expansion. Okay. Now as we have discussed in our previous slides also, that for reversible expansion the final pressure will be less than that of the initial pressure and volume will increase from V1 to V2. So suppose from point A to say point B, pressure has decreased from P1 to P2 and volume has increased from V1 to V2. And as we know, in reversible processes, the process is carried out in several small steps. That is a multi-step process. So we can see that here the change has been carried out in 4 small steps. And to find out the net work done, we should find out the work done for each of the small steps. Now let us find out the work done for the first step. Now say for the first step the pressure has decreased from P1 to say PA and volume has increased from V1 to say VA. Now work done is equal to volume change against the final pressure of that step. Now for the first step, what is the final pressure? PA. So this is PA, right? And this is the change in volume from V1 to VA. So what will be the work done? Work done will be this region. That is the volume change against the final pressure PA, right? Now for the second step. For the second step, say pressure has decreased from PA to suppose PB, correct? And volume has increased from say VA to VB. So what is the final pressure for second step? This is the final pressure PB, and the volume change has occurred from VA to VB. So work done will be volume change against the final pressure of second step, that is PB. So this shaded part will be the work done for the second step. And similarly the shaded portions you can see will be the work done for the entire process. Now we know reversible processes are actually carried out in several infinite steps. So actually if we divide this in several infinite steps, okay, several infinite steps. So these blocks will eventually become smaller and the shaded portion will be actually the whole area under the curve. So as you can see, the whole area under the curve is the net work done for reversible expansion. Correct? Now coming to irreversible expansion. Now we know irreversible expansion is actually a single step process. So in irreversible expansion, from point A to point B, the pressure has changed from P1 to P2 and volume has increased from V1 to V2, but this has occurred only in one single step. Now again we know work done is the volume change against the final pressure. So what is the final pressure? Final pressure is P2. This is P2 and this is the change in volume, right? So if we plot the work done, so this is the work done for irreversible expansion. So we can see the shaded portion is the work done for irreversible expansion. Thus, from the graphical representation, we can see reversible work done is greater than irreversible work done, because in reversible work done, the area under the curve is the net work done, whereas in the irreversible work done, only this portion is the net work done. So, for expansion, we can say in reversible work done, you will obtain the maximum work done, which we have proved mathematically in our previous slides. Correct? Now coming to graphical representation for reversible and irreversible compression. Now first you can see the plot for irreversible compression. Now what is the condition for compression? External pressure is greater than that of the internal pressure, right? So we can see that P2 will be greater than P1. Here P2 is greater than P1 and volume will decrease, that is V2 will be less than V1. So suppose from point A to point B, the change has occurred in single step as it is an irreversible process and pressure has actually increased from P1 to P2 and volume has decreased from V1 to V2. Now we know for the single step process, this is the final pressure, that is P2, and the volume change has occurred from V1 to V2. So this whole area under the curve will be the net work done, right? That is volume change against the final pressure P2. Correct? Now coming to reversible compression. Okay. Now we know reversible processes are carried out in several small steps. So from B to A, the pressure has increased from P1 to P2 and volume decreased from V1 to V2, and it has occurred in 3 small steps. Now if we find out the work done for the first step. So here pressure has increased from say P1 to PA and volume has decreased from V1 to say VA. So this is the final pressure for first step PA. So what will be the net work done? net work done will be volume change against the final pressure PA. So this shaded portion will be the work done for the first step. Now coming to the second step. So here pressure has increased from PA to say PB and volume has decreased from BA to say PB. So this is the final pressure PV. So net work done will be again the volume change against the final pressure. So this shaded portion will be the work done, right? So for all the three steps, the shaded portion will be the work done. Now we know reversible processes are carried out in several infinite small steps. So if we divide the entire plot in several infinite small steps, so we will get small blocks throughout the plot and the whole area under the curve will be the net work done obtained for reversible compression, right? Now as we have seen for compression, the irreversible work done is actually greater than the reversible work done. So as we can see from our graphical plots, the area obtained under irreversible compression is much greater than that of the reversible compression. So the statement is correct. Now also we have seen that for reversible process, expansion work is equal to compression work. So if we remember, in expansion also the reversible work plot was same as in the case of compression. That means that while you are traveling from A to B and expansion is occurring in this path, then this path can also be reversed from B to A and meanwhile compression will occur. That is, the path can be reversed, which is actually the condition for reversible processes. Now coming to irreversible process. In an irreversible process, expansion work is not equal to compression work. So as you can see in irreversible compression, this is the work done, while in reversible compression only this part was the work done, if you remember, right? This is because we know irreversible processes are unidirectional. The path cannot be reversed. So this statement is also correct, right? With this we have come to the end of the video. If you have any doubt regarding the basic terms or the sign conventions which you have not discussed in this video, or any other part that we have discussed in the video, then you can comment down below, and in the next video I will try to solve your doubts. Plus we will see some more topics of thermodynamics, and also we will try to solve certain numerical problems. Okay, so if you like the video, please like, share and subscribe to the channel. Thank you.